This is pre-AP Precalculus, notes 2.3, one-to-one functions, looking at them numerically, graphically, and analytically. A function is a relationship between x and y such that each x value corresponds to only one y value. If the point 2, -3 is on the graph of a function, then f of x, if the point 2, -3 is on the graph of the function f of x, then no other point can have an x value of -2. However, it's possible for another point on the graph to have a y coordinate of -3, even though this y value has already been used. So that still is a function. Each x value is paired with one y value, but multiple y values can be paired with, the same y value can be paired with multiple x values and still be a function. Well, what's a one-to-one function? It's a function in which each y value is paired with only one x value. A one-to-one function, every x and y that is in the domain and range is paired with exactly one number. It cannot be multiple pairings. For example, if 2, -3 and 5, -3 are both on the graph of f of x, and there is a y value, -3, that has more than one x value. Therefore, there is no way for that function to be one-to-one. We're going to examine this in three different ways: numerically, graphically, and analytically. Numerically, we are going to say if f of x is a continuous function, it is one-to-one if the function is always increasing or decreasing. Well, what does that mean? That means that if you look at the graph from left to right, it's always going up or it's always going down, never horizontal, and never changes direction from increasing to decreasing. It's always increasing or it's always decreasing. Second part, if f of x is a discrete function means you have a list of ordered pairs. Typically, you'll be given that in a table. So a discrete function is not continuous. We have one case where we have a continuous function. We have another case where it's not continuous, but it's discrete. If f of x is a discrete function, it is one-to-one if no y values are repeated. In other words, each x value has a unique y value, each y value has a unique x value. Graphically, to determine if a graph is one-to-one, we can use the horizontal line test. If you can draw a horizontal line and it never hits the graph in more than one location at the same time, it's a one-to-one function. Analytically, using equations and such, based upon the equation and what type of function f of x is, the shape of the graph should be known, and that's from us knowing parent graphs. And if we don't know what it is from the parent graph, then we would use our calculator to figure out what it looks like. The inverse of a function is defined to be the function formed when the domain and range of the function are switched. Simply put, if you want to find the inverse of a function, if it has an inverse, you interchange x and y, then you get y by itself. And if that is a function, that's the inverse. If it's not a function, then the original function has no inverse. What property of the function must exist in order for the inverse of the function to exist? Why? Well, f of x must be one-to-one if f inverse is to exist, because if f of x is not one-to-one, then the repeated y values of f of x would become repeated x values of f inverse. So let me just give you a visual of something like that. Let's say this was what f of x was. And let's say that this is the ordered pair -1, 1. And let's say this is the ordered pair 1, 1. Write this a little more clearly. This is a function, but these y values, 1 and 1, when you interchange x and y, that means that our new ordered pairs are going to be 1, 1, and 1, -1. So the graph would look like this. So if we try to find the inverse of this, it wouldn't be a function because the supposed inverse doesn't pass the vertical line test, which means the original function f of x wouldn't pass the horizontal line test. Moving on. If it can be determined that a function is one-to-one, so once you know that it's one-to-one, then the inverse of the function can be found. Fill in the following chart that will describe how to find the inverse of a function if it is established to be a one-to-one function. Numerically, all you got to do is switch the x and y values. Done, you found the inverse. Graphically, if you take the original function and reflect it over the line y equals x, that will give you your new graph. Now, you might look at this and think, wow, how am I going to remember both of these things? They're the same thing. This says right here, y equals x. Reading it from right to left, x equals y. This says switch the x and the y values. It's saying the same thing. It is very consistent, which means this is awesome to learn. Analytically, so if you have an equation, like this top one would be maybe if you have a table of values. This is if you have a picture. And this last one if you have the equation. Switch the x and y's in the equation. That's consistent with the first two. Solve the equation for y, and replace y with the inverse notation, which would typically be f of -1. Depends on the function. Let's look at some examples. For each of the following functions, determine if the inverse of the function exists. Provide justification. That's two things to do. If it does, find the inverse. It's three things we're supposed to do. If the relation is given in numerical form, give the table that represent f inverse of x. That's like a subplot to find the inverse. If the relation is given in graphical form, sketch it. That's also a subplot. And if it's given in analytical form, find the equation. Also a subplot. These things here are the three options if you determine that it has an inverse. Looking at A. So to determine if it's an inverse function, to determine if this function has an inverse, you first want to determine, is it one-to-one? So we're assuming it's a function because it says for each of the following functions. So in a table, are there any y values here that are repeated? The 2's are. And do those 2's go to different x values? Yes, this is not one-to-one. So I'm just going to write down what I just said. The y value 2 is paired with two different x values. What can we conclude from that? F of x is not one-to-one. If your function is not one-to-one, you can conclude that the inverse of the function does not exist. Part B. Same question, same directions, different table. We already know it's a function because we're told that in the directions. Are there any repeated y values here? There are not. Each y value is paired with exactly one x value. What can we conclude from that? F of x is one-to-one. If it's one-to-one, that means f inverse exists. So how do you make the table for that? Easy. You just take each of these x and y values and you interchange them. You will get a table like this, and I did miswrite something here. This should be f inverse of x, not f of x. Just switch all the x and y's. C, we are given this graph, and we're supposed to determine, does it have an inverse? And to first decide that, we need to figure out, is it one-to-one? So here's a fact. This graph is always decreasing on its domain. As you go left to right, we're going down the entire time. If it's always decreasing on the domain, that means this little fella is one-to-one. If it's one-to-one, then f inverse must exist. I made a table of the ordered pairs listed in this, we have negative 5, 5. I'll use arrows here. We got negative 2, 1. We got 2, negative 1. And we got 4, negative 4. To find the inverse, we take each of those ordered pairs, we reverse the x and y coordinates. This will find us the inverse. If you do that, that means that we are reflecting this graph over the line y equals x. So you can do that visually without making that table. Technically, this table here is optional because you were given a graph. But if I look at each of these points on this graph, and I draw a perpendicular segment and make the same distance on each side, which you don't have to do all this, I'm just trying to explain. You will find that each of these purple segments that I'm drawing, they're identical in length on each side of the line of symmetry. Let me get rid of all that junk. So there's C. D, to determine what the inverse is, we got to first figure out, is it 1 to 1? And guess what? This graph does not pass the horizontal line test. I could draw a horizontal line through here, through lots of places, and I'm hitting the graph in more than one location. What conclusion can we draw from that? G of x is not 1 to 1. What conclusion can we draw from that? G inverse cannot exist. The only way the inverse function can exist is if the original function is 1 to 1. Ichiro. This graph passes the horizontal line test. Therefore, the inverse exists. Pardon me. Therefore, the graph is 1 to 1. Then, therefore, the inverse exists. So if I were to draw this little fella, these little dashes aren't supposed to be here, by the way. So we're originally, this is the line of symmetry. This goes for that last one too. I think those little marks were there. It's supposed to be dashed because it's not part of the graph. Let me fix that for this past one too. If you draw those little dashes, I'm sorry. That didn't really work out, did it? There we go. Line of symmetry should be dashed. So if you can visualize this, and it's, you know, not the easiest thing in the world, but if you take each of these points and reflect it across so that your segment hits the line of symmetry at a perpendicular, I mean, we can do this an infinite number of times. I would minimally do it to those points that are marked. If you do that, we're going to get this other part here. If you're thinking, that's way too hard, I can't do that. Well, if you can't do that, then make this table. This table is required if you're given the information as a table. It's an optional thing that you can do if you're given a graph and you're having a hard time reflecting it. F. Here we're given a function. Well, you have to think to yourself, if I were to graph this, what would it look like? This would be a parabola that would not pass the horizontal line test. If it doesn't pass the horizontal line test, then this graph, this function f of x is not 1 to 1. If it's not 1 to 1, f inverse doesn't exist. Next one. This is a linear equation, and it's not horizontal. So are all linear functions 1 to 1? No. All linear functions that are not horizontal would pass the horizontal line test, because a horizontal line wouldn't pass it. This is 1 to 1. Therefore, the inverse exists. How do you find the inverse? Well, you take your function, you interchange x and y. You then manipulate the equation until you can get y by itself. to be clear, from here to here, I multiplied each term by 5 over 2. That cancels with this fraction. Here we get 5 over 2x. Here we're going to get 5 times 3, which is 15 divided by 2. That's why I got 15 over 2. Replace the y with f inverse. That's the inverse of that function. H. This is a half of a parabola that opens up to the right. It's a square root function. That passes the horizontal line test. As a result, that makes this function 1-to-1. Since it's 1-to-1, G inverse exists, which means we can find the inverse. I should mention something now. I'll mention it again at the end. You all should know what this graph, what the vertex of this graph is. It's negative 3, 4, and it still opens up and to the right. The domain for this function is going to be from negative 3 to infinity. The range for this function starts at 4 and goes up forever, 4 to infinity. This is for g of x. Probably better if I write that down here. Now, why does that matter? You'll see in a moment why that matters. So if we interchange x and y, because the direction said find the inverse, we get this. If we subtract 4 from both sides, and if we multiply both sides by half or divide both sides by 2, whichever you'd prefer. Now I intentionally, when I went from here to here and multiplied by half, I left this in parentheses because, as we've learned before, if the coefficient of x is a 1, it's easier to graph. That's why I intentionally put that on the outside. And if you square both sides, the right side, the square root goes away. If you subtract 3 from both sides, you get this. Now, if you were to graph this, this would be a parabola with the vertex at 4, 3. Did I make a mistake? I feel like it should be, I'm sorry, 4, negative 3, yeah. So here's the reason why I was panicking when I got 4, 3 as the vertex. It doesn't make any sense because if the original graph had a vertex of negative 3, 4, the inverse, you should be able to switch the x and y and get the new vertex. So it's a good thing I panicked because it made me realize I had made a mistake. That's a negative 3. What would this graph look like? It's a parabola that's going to open up, right? Well, what's the problem with this? Does this resemble this graph? No, it's only supposed to be half of that. Well, which half are you supposed to use? The original function had a domain, had a range of 4 to infinity, which means this little fella is going to have a domain of 4 to infinity. Original function's range is the inverse function's domain. So that's why when we write this in function notation, G inverse, we have to say, hey, by the way, we only want x values that are greater than or equal to 4. That's why I have this ask y here. So in class, we would discuss this question as a group. Long story short, if the original function's range is not all real numbers, you're going to have domain restrictions when you do the inverse. All right, let me get rid of this and let me write this stuff out instead of me just bringing this up. We have the function g, we're supposed to find its inverse. Any domain restrictions here? No. Does the range go on forever? Yes. This function is actually just 3 halves x, just a line. It's just written in a weird way, minus 2. If you wanted to do that, you could. I divided both top numbers by the numerator by 2. So to find the inverse, I'm going to interchange and put x in for y and y in for x. Then I'm going to solve the equation for y. I'm going to multiply both sides by 2, get 2x plus 4 equals 3y. Divide each term by 3, get 2/3 x plus 4/3 equals y. So G inverse 2/3 x plus 4/3. You could have written it as 2x plus 4 over 3. It's acceptable. The next one, find G of G inverse of x. I'll just use the original form here. So G of G inverse. You know what? Now that I see what I'm going to do next, I'm going to rewrite this as 2x plus 4 over 3. It's going to make my calculation easier. I'm going to be putting 2x plus 4 over 3 into the original function. When you substitute, you really should use parentheses. Now we are taking 2x plus 4 and we are multiplying it by 3 and dividing it by 3. So those are inverse operations, they cancel. So we get 2x plus 4 minus 4 over 2. Plus 4 and a minus 4 inverse operations, they cancel. Then I'm going to get 2x over 2. That reduces to x. That's interesting. G of G inverse of x is just x. Weird, wacky stuff. G inverse of 3x minus 4 over 2. Supposed to put function g into function G inverse. So it's going to be 2 times 3x minus 4 over 2 plus 4 over 3. So just to make sure I did that right, I should have 2 plus 4 over 3 and replacing x with 3x minus 4. Similarly to the last problem, multiplying and dividing by the same number, inverse operations, they cancel. So we get 3x minus 4 plus 4. And that's being divided by 3. Plus and minus 4's cancel. We get 3x over 3. That's going to give us x. So G inverse of G of x, oh, that's also x. Huh. That is interesting. Coincidence? I don't think so. If two functions f and g are inverses of each other, then there are two special composite functions that will equal the same thing. F of g of x will be x, and g of f of x will also be x. This works every time you have two functions that are inverses. We have two examples of such things. Here, I'm going to replace, in function f, I'm going to replace the x's with g of x, which is x minus 3 over 2. The 2's cancel, so we get x minus 3 plus 3. The 3's cancel, and we get x. If I do something similar and do g of f of x, that also reduces to x. When it says determine if the pairs of functions are inverses, you have to do both these compositions. Well, if one turns out to be x, do the other one, see if it also ends up being x. What can we conclude from this? Well, we can conclude this is something you would need to do on like a free response question. F of g of x is the same as g of f of x, which is x. What conclusion can we draw from that? F and g are inverses of each other. Look at example B. If we try to do this one, we're going to find that the best we can do is simplify that to x minus 2. If that doesn't simplify to x, there's no point in checking g of f of x. It doesn't really matter what it simplifies to because they both have to simplify to x. Conclusion, f of g of x is an x. Therefore, f and g are not inverses of each other. That concludes the notes. Thank you for paying attention, and have a good one. Have a good one.